Okay, we've been discussing about memory, and in this segment, we're going to look at paging. So, before we get into paging, to get some context on what this is and how it works or why we need this, let's go back to this variable partition memory allocation scheme which we were discussing previously. So, the details of this thing, what it is, how it works, what problems it causes, we discussed in a separate segment. So, I am not going to go into all that again. But one thing I would like to recall from our discussion on this is that the memory allocated to any process has to be contiguous, right? So, that is the reason fragmentation and all comes up, because if you have a process which requires, say, 12 spaces of memory, you have 5 over here and 7 over here, you cannot allocate that way in this variable partition scheme, because the space you allocate to any process needs to be contiguous, and because of that we have different types of fragmentation and so on. So when we come to this system called paging, what we do is we try to see if we can actually break that rule. What if I can allocate discontinuous or disjoint intervals of memory to a process in such a way that I still keep track of what is allocated to which process, and I make sure there is no confusion, but I break the rule or break the necessity that the memory allocated to a process is continuous. So how that is done is what paging talks about, that we'll come to. But how is that going to help is, see, if you allow processes to have disjoint or discontinuous memory intervals, then to a great extent you can overcome fragmentation, right? Both internal and external. So you can allocate this part and this part to a process if necessary. So these holes, this wastage will not happen. So if you can come up with a paging strategy or some strategy that ensures smooth, hassle-free allocation of discontinuous memory segments to processes, then you have effectively solved the problem of fragmentation and memory wastage. So such a process is called paging. Within paging there are multiple types. We will for now be looking at the most basic method. So the basic method of paging involves, so what is paging first of all is when you try to allocate memory permitting the process's physical address space to be non-continuous. That's what paging is. So when you allocate physical memory to a process, generally in variable partition scheme we saw that it needs to be continuous. So when you come to the next scheme, which is paging, you are removing that rule. So you're saying that constraint is no longer enforced. Memory need not necessarily be contiguous. You can have discontinuous intervals of memory. So how exactly do we implement that? What are the logistics? We will take a look now. Right, so as I said, we're going to look at the most basic method of paging. So what happens here is, your physical memory is divided into fixed size blocks called frames, and logical memory is divided into blocks of the same size called pages. So as you know, we have the physical memory, which is your actual RAM, main memory, and we have our logical memory, which is your hard disk or whatever. So you divide both of these into blocks or segments of the same size. So if you are dividing your logical memory, your hard disk, into blocks of say 32 bits each, then you will divide your physical memory also into blocks of 32 bits each. So the size will be fixed. And now the blocks in the physical memory or in your RAM are called frames, and in your logical memory they are called pages, right? So what are we doing? We're taking your entire logical memory, which is let's say 64 GB or whatever, and you're dividing that into blocks of the same size, let's say 32 bit, 32 bit, 32 bit, 32 bit. Each of these blocks is called a page. Similarly, you're taking your physical memory, your RAM, you're dividing that also into blocks of the same size, 32 bit, 32 bit, 32 bit, and these blocks we're calling it frames. So the size should be the same. If your logical memory page size is 32 bits, your physical memory frame size should also be 32 bits. If this is a 64 bit, this should also be 64 bit. So that division we're doing, and then obviously every page of the logical memory will be mapped when necessary to a particular frame of your physical memory. This is very similar to you know the mapping between your main memory and cache memory, which you would have studied in your computer organization, if I'm not wrong. There are multiple ways of caching, right? There is direct mapping, there is something called set associative mapping. There are different ways. In direct mapping, you have this thing goes to this location of main memory, goes to this location of cache memory, so on and so forth. That kind of thing only. So here you have this location of logical memory, this page of logical memory goes to this frame of main memory, physical memory, and that information is stored in something called a page table. So the page table is going to help you do the mapping between pages and frames. So this page number of logical memory corresponds to this frame number of physical memory. That mapping is going to be done by something called the page table. So the page table has multiple entries, of course. Each entry consists of two parts, a page number and a page offset. So again, if you remember in your cache memory mapping schemes, in some you had this thing called a tag bit, which sort of acts like an index or an identifier kind of thing, which helps you identify if multiple main memory locations are allocated to this cache memory location, which of those is currently in the cache, that kind of thing, right? So similarly, offset is going to help you identify something. We'll see what it is. We'll take a look at this picture right now. So this is how paging, the mapping works. Okay, so what happens is your CPU first takes the logical address. So the logical address is made up of the page number and the page offset. If you see here, there's the page number and the page offset. So we'll see what they are. Page number obviously refers to which page of the logical memory this data is stored in, right? Logical memory, as I told you, is divided into pages. Let's say you have 64 GB of hard disk or whatever, which is just an example. I'm not sure if 64 GB is a valid size for a hard disk, but yeah, just for an example, that you're dividing it into blocks of 32-bit, 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 32-bit. Each is called a page. So you have page 0, page 1, page 2, page 3, so on up to probably some few million pages or whatever, right? So from that, page 0, the page number will be 0. For page 1, the page number will be 1. Page 2, the page number will be 2, and so on and so forth, obviously. So that is the page number. And then you have something called the page offset, which I will come to in a minute, right? So these two constitute your logical address, which is generated by the CPU. Now what is done is, the CPU takes the page number and sends it to the page table. From that, it takes the corresponding frame number. So the page table, as I told you, is going to give you the mapping. It is like the index page of your book. So it says this chapter, you go to this page number. This subtopic, you go to this page number, right? That's what the index of a book does. So same thing, page table says this page of logical memory, go to this frame number of physical memory. So if you want page 5 of your logical memory, go to frame number 6 of your physical memory, for example, random. So that mapping is used. The CPU refers to the page table. It takes the page number, it checks the entries one by one until the page number is matched. It looks at the corresponding frame number. It identifies which frame to go to. Now you have the frame number. The page offset is directly carried here as such. So now this is going to help you identify your data in the physical memory. So what is this offset doing? So I said your frames and pages have a fixed size, right? So for example, I said 32 bits. We'll continue with that example. So you had a page which is 32 bits long in your logical memory. Some page number. I looked at the page table and I mapped it to some frame in my physical memory, which is also 32 bits long. Right, so now I know it is within these 32 bits that the data I am looking for lies. But within those 32 bits, which particular bit contains the data I am looking for? You might not need all 32 bits, right? So you look at the index, looking for a topic, you go to that page number in a book. You might not need everything that's written on that page. You might be looking for one specific paragraph or one specific point or one specific thing given in a box on the side or something like that, no? So within these 32 bits, which bit or which bits am I looking for? So that is what your page offset indicates. So if page offset is 4, for example, of course all of this will be stored in binary. So when I say 4, 5, 6, please don't assume that the actual decimal numbers will be stored there. So if it is 4, the binary equivalent of 4 will be stored there. That assumption goes without saying. So if the page offset is 4, it means I'm looking for the 4th bit of this frame. So that is how the most basic version of paging works. So your logical address consists of a page number and a page offset. Page number refers to the location in logical memory that is taken, compared in the page table. Frame number is found out, which refers to location in physical memory. The offset tells you within that location which bit you have to access. So using the location and the particular bit number, you can reach your data, you can access it, then you can read, write, do whatever. So that is the basic method of paging.